Welcome to Learning to Engineer. Imagine you are watching a video. Whatever is desirable contents that you are receiving, maybe the voice or maybe the visual contents that you are seeing, the desirable stuff that is there in whatever you are watching is called as the signal, and the undesirable noise, the air noise, the background horns and other stuff, they are called as noise or disturbances. In this video, we are going to talk about signal to noise ratio. What is that? The ratio between the signal and the noise is signal to noise ratio, as you all know. It is self-explanatory. But beyond that, we need to know what is the signal strength, what is the noise power, and how good it is and how good should the signal be before we transmit to a system. Imagine that a signal containing noise is input to an amplifier. What will happen to the output from it? How good will it be? How good in terms of the signal strength will amplifier's output contain? All that we are going to discuss in this video, and at the end of this video I'll be explaining you how to remove the noise components from a signal. I'm just going to use an application called Audacity for it. I'm not trying to promote any content or advertise any content. It is just for your information. Let's get started. The signal to noise ratio is represented as SNR. The signal to noise ratio is the signal's strength square divided by the noise strength square. This is called as signal to noise ratio. This varies for different signals, and there are some certain digital filters or analog filters that will eliminate the noise near to zero and give you a good quality output. The noise is characterized by a noise power, which is power of the noise is Boltzmann constant times the temperature times the frequency of the signal. So from this equation you can understand that the noise power increases with respect to temperature. Greater the temperatures, higher will be the noise. Imagine that you are using a voltmeter at India, and imagine you are using the same voltmeter at a cooler place than India. So in warmer places the noise will be more, meaning that your signal will be affected by this noise. But if you go to cooler places, this noise will be less. The signal to noise ratio is affected by the noise power. The noise power is Boltzmann constant times the temperature times the frequency. Boltzmann constant is 1.38 10 to the power minus 23 joule per Kelvin. This is Boltzmann constant. If you want to know more details on this constant, let me know. I will make a separate video on that. For per degree rise in temperature, what is the energy that is occurring because of it? So based on the temperature and the frequency, the noise power varies. Based on this noise power, the signal to noise ratio varies. It is sufficient for you to know just this amount of information when you are trying to solve problems on signal to noise ratio. A voltmeter has an input resistance of 15 mega ohm. How much noise voltage will it generate for each cycle of frequency bandwidth at 17 degrees Celsius? The Boltzmann constant is 1.38 into 10 to the power minus 23 joule per Kelvin. In this problem, the temperature is given as 17 degrees Celsius. We need to convert that into Kelvin because the noise power is in terms of Kelvin. So basically the Boltzmann constant is joule per Kelvin. When temperature is in Kelvin, the dimensions will cancel and the power will be joule by second. So this is the idea behind converting the temperature from degree Celsius to Kelvin. Okay, so in this problem the temperature is given as 17 degrees Celsius or 17 plus 273, which is 290 Kelvin. So this is the temperature that is given to us. Next, the resistance of the voltmeter is given as 15 mega ohm. So what is asked? We are asked to find out the noise power for one cycle of frequency, and it is given that frequency is 1 or per cycle of frequency. The Boltzmann constant is given 1.38 into 10 to the power minus 23 joule per Kelvin. So it is a direct substitution. The noise power is 1.38 into 10 to the power minus 23 times 290 times 1. The noise power is. We are asked to find out the noise voltage of this voltmeter. Basically, this voltmeter contains a signal and some noise due to the temperature effects. So, the noise power is this 400.2 into 10 to the power minus 23. So, we are asked to find out the noise voltage. Power is nothing but voltage square divided by 4 times R. This is the according to maximum power transfer theorem, this is the power that is transferred. We are asked to find out this voltage or the voltage that is measured by the voltmeter. Okay, we know the noise power to be 400.2 into 10 to the power minus 23. So this implies V square is 4 into R. What is R? The resistance is given as 15 mega ohm. So this is 15 into 10 to the power 6. 4R into 400.2 into 10 to the power minus 23. So this is the voltage that is across the voltmeter when there is noise interferences. We will solve one more problem for better understanding. This is a simple one just for you to get an idea about noise power. I just solved this problem. We are going to solve another problem for you to get a better idea on signal to noise ratio. At the input, an amplifier has a signal voltage level of 3 microvolt and noise voltage level of 1 microvolt. What is the signal to noise ratio at the input? Next, if the voltage gain of the amplifier is 20, what is the SNR at output? Next, if amplifier adds 5 microvolt of noise, what is the SNR at output? Calculate the noise factor and noise figure. Noise factor is nothing but the SNR or the signal to noise ratio of the input signal divided by the signal to noise ratio at the output, and the noise figure is 10 log noise factor. This is noise figure. These are just formulas. Let us first jot down the given data and then find out what is asked. The signal voltage is given as 3 microvolt and the noise voltage is given as 1 microvolt. Usually I represent this as XS, which means these are the input quantities. The input signal is 3 microvolt, the input noise is 1 microvolt. What is the signal to noise ratio at the input? That is our first question. It is just formula substitution, which is 3 microvolt whole square divided by 1 microvolt whole square, which is, so the signal to noise ratio at input is 9. Basically what is happening, this input signal, I am just marking it to be X. This X is passed through an amplifier. This X is passed through an amplifier and then you are getting some input. There is some signal and there is some noise at the input. Due to that, the signal as well as the noise will get amplified by the amplifier, and then you will get the amplified version of the signal and then the amplified version of the noise. So, in the second subdivision, we are asked to find out what is the signal to noise ratio at the output when the gain of the amplifier is given as 20. Meaning that 20 times the signal will be amplified and 20 times the noise will also be amplified. The signal to noise ratio at the output will be the signal strength square divided by the noise Yn or the noise strength square. We have to first find out Ys and Yn. Y is 20 times X because the amplifier gain is given as 20. So, the output signal is 20 times the input signal, which is 3 microvolt. So, the output signal is 60 microvolt. And then Yn or the output noise is 20 times the input noise. Usually what students do, they just amplify the signal forgetting the noise. Whenever you are passing any signal to a system, it may be an amplifier, it might be a recorder, it might be anything, it will be working on the signal as well as the noise. unless there is a noise filtering device that is there inside the system, you won't be able to differentiate the signal and the noise. So basically the gain of 20 will be applied to the signal as well as the noise. So the noise will also be amplified 20 times. So the noise is 20 microvolt. So what is the SNR at output? Y square, which is 60 microvolt whole square, divided by 20 microvolt whole square. So this is nothing but 3600 divided by 400. So the signal to noise ratio at output is also same. Okay, so whenever you have an amplifier and it is amplifying the signal as well as the noise, the SNR at input and the SNR at output will always be same, because it is linearly amplifying. It is multiplying this by 20 times and it is multiplying this by 20 times. So in that case, when you are dividing both of them, the 20 factor cancels out. The signal to noise ratio at input and the signal to noise ratio at output of a good amplifier is always same. Let us think about the third subdivision. What is asked? The amplifier is adding 5 microvolt of noise. Remember, I said to you, if the amplifier is a good device, meaning that it doesn't add any noise, so in that case both the signal as well as the noise is getting multiplied by 20 times. But when the amplifier adds some noise, here it is 5 microvolt, right? So what will happen? The signal will be Ys will be 20 times the input signal, 3 microvolt, which is 60 microvolt. What about the noise? The noise will be 20 times the input plus the amplifier's noise of 5 microvolt. So this is 25 microvolt. Let us see what is the signal to noise ratio when amplifier is adding some noise. When the amplifier is adding some noise, the SNR at output will be 60 microvolt whole square divided by 25 microvolt whole square. This will be 3600 divided by SNR at output will be the signal to noise ratio was 9 when the amplifier was good. When the amplifier doesn't add any noise, the SNR ratio was 9, and when the noise is added by the amplifier, what is the SNR output? It is just 5.76 in this case. We are asked to find out the noise factor and noise figure. The noise factor is the SNR at input divided by the SNR at output, which is 9 divided by 5.76. Next, what we are asked to find? We are asked to find out the noise figure. The noise figure is 10 log F. So this will be 10 log, what is F? 1.56. So this is the noise figure. First, for the system we calculated the SNR at the input, meaning that the signal to noise ratio before it is getting amplified. So next what we found? We found out the signal to noise ratio at the output when the amplifier didn't add any noise. So in that case the SNR at the output was also 9. When the amplifier is adding a noise of 5 microvolt, we had the third case. We had the signal to noise ratio at output as 5.76. Next we found out the noise factor, which is the SNR at input by SNR at output. So the noise factor is 1.56. What is noise figure? 10 log F, which is 1.93 dB. Yeah, so now we have found out noise factor as well as noise figure. Now I am going to tell you how to remove the noise using Audacity. Observe this video, you will be able to hear a background noise that is playing here. I will be telling you how to remove this noise. So this is the pH level of you are hearing a coarse noise in the background, right? I will be telling you how to reduce this noise. For that, you need to install an application called Audacity, wherein you have to first import this audio. Even though you have this as a video file, it doesn't really matter. You can just select the video file and it will automatically convert it into MP3 file. So I have to first select the section of this audio which contains that noise. Let me first zoom the timeline so that I can see those waves clearly. I'll start playing from here.
So this is the pH level.
I think by this time you will be able to hear that coarse noise very
case,
clearly. So I'm just selecting this portion of the noise which has to be removed from my audio. Go to Effect and then select Noise Reduction. Here, this software will be analyzing the noise profile of your audio. You can just check how much noise should be reduced. You can increase this or decrease this. But be careful, if you put it somewhere close to the maximum, your voice will sound muffled. The actual signal's quality will be reduced. We only want the noise quality to get reduced. So I'm just setting this dB to 32. And the sensitivity is fairly high actually. You can reduce it. If you reduce the sensitivity, it will not pick up the similar noise which doesn't have this much level of loudness or the selected level of loudness. So I usually keep this to 17. You can just try out different options and check how good the noise profile is. So after you set the noise reduction, sensitivity and the frequency, how much to be smoothened, I usually keep this to 0 and then click get noise profile. So the software will now analyze the profile of the noise which is being selected now. So I want to remove similar noise from the entire structure of this video. So what I will do, I'll just go Ctrl A or select the entire timeline and then go to Effect, Repeat Noise Reduction or press Ctrl R. Once you do it, the Audacity will remove the parts of the noise which is there throughout the video. If you can observe, you won't be able to see any waves in this region. Earlier you had some waves or you had some noise in this. So let me just click play.
So this is the pH level.
So you are hearing the audio in a very crisp manner, right? The noise has been removed now, and now what you can do is you have to export this as MP3. Since you want a video output, you can export this as MP3 first and then merge it with the video file. You have to export it as MP3 and then you can save it as, say for example, my audio. You can just keep any name that you want. You can save it as MP3 file, you can save it as MP2 file, AC3 file or any other format that you want. And then just click save. So the file will get exported. If you want, you can save this project. I usually not save my Audacity projects because I mostly use it only for noise reduction purposes. You can just select the audio from the place where you store and you can just listen to it. You will be able to see that the audio is very crisp.
It will not turn.
So thanks for watching. Let me know your thoughts in the comment section. Do give a thumbs up if you like this video. If you have any other topics in your mind or if you want any topics to be featured in this channel, tell me in the comment section or you can email to learningtoengineer@gmail.com. Thank you.